Okay. Now we're live. So good afternoon, everyone. I know it's been a long day and it's already late in the day. So I have full understanding if you're now already a bit full with information and impressions after a whole day here at the battery show. However, I hope that I have some interesting insights for you, and I really appreciate that you take the time coming by and listening to my presentation. So first of all, I'd like to introduce myself. My name is Sabrina Rathgeber. I'm leading the sales in Bosch Manufacturing Solutions. And today I'd like to give you an overview and a presentation about our approach on how to increase efficiency in battery manufacturing. So at the very beginning, I just want, for those who haven't heard of Bosch Manufacturing Solutions yet, give a brief overview and an introduction about Bosch Manufacturing. And I promise it's only the one slide. And to be honest, I've been in sales now for a while, and many people still don't know that Bosch Manufacturing exists and what Bosch Manufacturing is doing. And the reason why is, even though we're existing since more than 30 years, the majority of the time we spend in serving Bosch plants with our production equipment. So actually, in contrary to Bosch Rexroth, who's supplying components, we are a turnkey special equipment provider. Back in the days, we were founded actually because Bosch has a long history in having huge effort and expertise in research. And they kind of struggled very often on how to bring new processes and new products into the production. And this is actually why we were founded back then. And until now, this is somehow still describing the core and the heart of our value proposition. A colleague of mine used to say, we want to understand the product and the processes, and then we build the machine around accordingly. And I think this is still the major differentiation to other integrators from what we do. So processes is really the core and describing the majority of our value proposition. Now, looking in a bit deeper, what are the challenges we are facing today? So first of all, we are all facing a challenge with the time to market. Time to market decreased tremendously the last years. If we look into Europe, we're now talking for fully integrated line of delivery times, 12 months or even less. And if we look to China, the delivery time is even shorter. So very often we see here expectations in delivery time, which is around 4 months. So there's a high speed in the industry, and we have to cope with that. Second topic we are facing all, being us as an integrator, being our customers as manufacturers of battery cells or batteries, we have a huge cost pressure and a high competition, because nowadays we're facing many competitions coming out of Asia, and with that also coming a high cost pressure on all our products. And the third challenge for us, especially in this segment, is that we have a high complexity in the machines and in the processes. So we're not even talking about different module designs and pack designs. It actually starts at the very beginning, having a complete variety of different cell formats, which we have then to use and to work with in our lines. So this is also bringing the challenge that we have to cope with variances in the products fed into the machine, but also the processes we have to apply in the machine. All in all, we are under the impression that to master this challenge and to come faster and cost competitive, the manufacturing itself must become radically more efficient and cost effective. And for the rest of the talk, I'd like to guide you on how our approach is to master that challenge. So today I brought two examples which I will tell you some more details. The first one is first-class automation technology. So it's still on how we build up machines, on concepts, on the processes, and on the application of them. It's not just about being fast. There is still something we can leverage in that matter. The second topic, what we see becoming increasingly more important, is what we call the software-defined production systems. So it's about how AI, how software is helping us in the engineering process, but also later on in the production, to be more efficient, to be more centered to the product demands and needs. So for the first half, I'd like now to step a bit deeper into what one of the latest examples in first-class automation technology we have. We're actually talking about a solution which we call fast cell preparation. And why are we under the impression that we needed such a solution? Especially if we now look into round cell feeding. And you think about a bigger cell to pack with cylindrical cells. You have easily 1,000 cells in one pack. And it's not just that you have to handle them and put them into the pack. The challenge also comes in bringing all these 1,000 cells identified, measured, and perhaps maybe cleaned into the line. And there you're facing them that you have to handle these cells in 0.2 seconds or even less in order to run the equipment in the expected cycle time. So besides this challenge in the cycle time, we are also facing that we wanted to have a flexible solution because with time to market, but also in terms of cost, we need a flexible solution which we can adapt to different cell formats and also to different cell types. So these were actually the basic preconditions when we started with this R&D activity. Technically, there are basically two challenges which we had to handle. So the first is the beginning of line testing. There especially the test speed and the data handling becomes a challenge. Because it's not just that you quickly give an impulse on the cell. There are some measurement procedures where you need a longer cycle time. And in the end, then also you have to have the data handled, analyzed, and put away. So this is something which is very often underestimated, but if you have so many cells running through the process, you also have to have an idea on how to handle the data later on. To deal with the targeted cycle time, we were very clear from the very beginning that it's not an option to stop and grip and fix the cell before the measurement. So our target was to find a solution where we can do the contacting and the measuring while the part is moving. But this is also for sure bringing some challenges with it. And the third topic is also the positioning and the reading of the DMC, because we have cylindrical parts, we don't know in which position the DMC is, and we have to be sure that we find it and that we have the chance to read it within the required cycle time. The third challenge we faced is cleaning. Plasma cleaning is not so complex, but every now and then we also face that we have to do laser cleaning or even laser structuring, and there we have to ensure that we first can cover all these different surface treatments, but second, that we also have a complete processing of the cell with minimum overlap, because for sure we don't want to miss a sequence of the part, but also we don't want to have a big overlap. Now looking a bit into what our solution provides. So we have for both DMC reading, BOL testing, and cleaning a continuously concept, where the DMC reading is kind of a linear mode, but BOL testing and cleaning are realized in a round table. Overall, this concept is modular, so we can either adapt different types of cylindrical cells, but also we can adapt different process modules to the basic machine concept. And therefore, we can combine all these several processes and also inspection steps within one compact system. And even with this concept, we're actually able to be flexible in terms of scale-up. So usually we have not so big volumes during the ramp-up phase of the line. So with the concept, we then can maybe install just one process part, which is then sufficient for the desired output during the ramp-up phase. But once we're achieving the peak line of output, with that concept, we're then able to just add additional process sources and process systems without touching the base of the machine and increasing the output. So with the machine itself, we will just run it faster and put additional process modules inside. With all that, we actually achieve a cycle time which is less than 0.18 seconds per cell, which is then in the end helping us to realize a throughput of 350 cylindrical cells per minute. Now looking a bit deeper on how we technically realized it. For the DMC, as I already stated, one challenge was how to ensure that we read and find the DMC while the part is moving. And to get a good solution for that, we actually worked with a systematic approach of a morphological box system, where we challenge different handling concepts, different lighting and reading concepts in order to find the best solution which is suitable for our requirements. And in the system, we have realized here we now have a master-slave system incorporating 3 cameras, while the cell is moved in a star wheel. For the beginning of line testing, fast contacting, especially as diverse testing requirements, are one of the major challenges we had to face. So usually for ACIR, it's not such a big deal because ACIR measurement usually takes around 100 milliseconds. But also we are asked that customers want a DCIR test on their cell as quality inspection before they feed it into the line. And as of now, DCIR test time is 2 seconds. So if we now talk that we want to realize a cycle time which is less than a tenth of that, we had to find different solutions. And for that, we have actually our own measurement system with own developed hardware, which is enabling us that we achieve this short cycle time, even while the part is moving. And also, we are not having issues with the cable length or the movement of the cables while it's moving. So all these development tasks help us here for both before line testing as well DMC reading to achieve this really, really short cycle time. But there were additional challenges, as I already stated. Cleaning of the head and the cylindrical surface. At first it sounds like an easy one, but the thing is, again, the cycle time, which is quite a challenge. But the other topic is, if the part is moving underneath the laser head, usually the center of the part is not in the center of the scan field. So even if the video does not really look that spectacular, but what we tested here is if we have a decentric alignment between the scan field and the cell, if we're still able to, in this case, apply super perpendicular lines into a cell, and we were able to do so. So how did we do that? First, we use for the overall output in the end multiple laser sources, which are actually sequentially set up. But for getting the accuracy and the repeatability, we used our own developed so-called scanner control engine. Scanner control engine is something Bosch developed already around 10 years ago, which is a own laser scanner, and this is giving us the freedom to really attach the process to our demands. So this was the one challenge with the cleaning, the accuracy and the repeatability, because we need to be sure that, especially if we do laser structuring, that we achieve the quality of the surface, but also that we don't have a too high overlap. But then another topic popped up. So another issue we're having, especially if we do laser processing, is that we have then residues up in the air coming from the cleaning process. And if you now imagine that the part is moving, it's also a bit of a challenge on how to make a particle exhaust. Here with our laser team and our competences we have on board, we made different airflow concepts, first based on simulation, later on with trials with 3D printed parts, to be really sure that the suction is working in an appropriate way. And the other challenge we were facing is usually we have a certain non-productive time. So we send a signal, or we have a position where a signal starts, and the signal is then kind of given to the laser that the laser power is switched on. Usually this time is kind of limiting, especially if we talk about the application we have right now. So again, we were then challenged on how we can overcome that we have a minimum of laser sources, but still achieving the desired output. And in the end, we find a solution where we actually have a trigger which is coming from the hardware, not from the software, but again, using the BMG scanner control engine. And with that combination, we were actually able that we have repositioning, restart, and PLC communication in less than 20 microseconds. So compared to conventional systems, actually we reduced the non-productive waiting time by more than 90% with that solution. So to conclude what we did in the fast cell preparation, besides the topics I already mentioned, due to the high throughput, but also due to the compact way on how we built the machine, we have a significant reduction of the footprint of the line. So actually we talk about roughly 50% of reduction in required floor space with a comparable throughput. Due to the modular design and also to the high standardization in the concepts and also challenging low-cost components being incorporated here with this specific application, we were actually able to reduce the cost by 60% compared to the standard solutions we had in our portfolio beforehand. And for sure, due to the high standardization, we're also going to have a shorter delivery time. In the end, as the system is scalable, it's really a good solution for our customers because until we haven't reached the peak production line, we don't have to do full investment. So with respect to the CAPEX, you don't have to invest all the CAPEX in advance for this specific part of the line. We can adopt it easily, and the only thing we have to add are different process modules in case we want to increase the output rate to a total maximum of 350 cells per minute. So this is now the example more on the hardware side of our portfolio. Now, I'd like to jump with you a bit deeper in the software-defined production systems. Here I'd like to start with a small question. So what is actually making a production line not just smart, but intelligent? Many companies are already talking about smart production line, and in our means, in our term, smart means that the line is interconnected. So we do collect data from all the machines, we also have a visualization of the data, and we have a hard-coded logic and simple algorithms applied onto the machine. You might think this is state-of-the-art, but honestly, sometimes if we really look deeper, this is not 100% available in the field yet. But still, this is not what we are talking about now, because we are not just talking about smart production lines, we are talking about intelligent production lines. And what's the difference now between smart and intelligent in our means? We have also dynamics then incorporated into these production lines. So we really use digital twins and simulations. I mean, that's an easy one, and everyone is promising it, that we have a digital twin and we make something like virtual commissioning during the engineering phase. But the basic benefit is coming if we then also use this digital twin later on while the line is running and challenging and mirroring all the results and data we collect along the line. And if we then also apply artificial intelligence algorithm on that, we can detect correlations and wide patterns over the complete production line. If we do so, then we can end up that we have a production line which makes autonomously decisions regarding the processes. And the thing is, this is not future. I have today here with me an example where we already have this exactly into production. Now looking a bit deeper into our digital value proposition. And don't be afraid, I know the picture might look a bit complex at the very beginning, but it's not as complex as you might think, because in the end we have two halves of this picture here. On the upper half, we're actually talking about everything what we call the engineering digital twin. So everything you can see on the top here is basically what we use in our engineering tool chain in order to be faster, to have more robust solutions, and also in order to help our customers to get a deeper understanding on what they will really get in the end. On the bottom of this picture, you see everything what we might call, or what we call, the operational digital twin. So all these applications here are then really operational and running on the productive equipment in the manufacturing. So we here have a portfolio of different applications for our customers, which we call the Intelligent Production Suite. Different apps, different use cases, you can decide if you need them. And in addition, we have here on the bottom left, something what we call the system operations. And here you also find something like the self-adjusting machine. I brought now two examples for today. I'll start with what we do in terms of virtual commissioning and digital validation. The first one might again sound being an easy one. It's value stream simulation. And yes, many companies already talk about value stream simulation. But the thing is, we need to start with that on a long-term modeling. So we also take experience what we already have from the equipment here into incorporation. And these solutions we have in place here help us, for example, to make a performance optimization of the line. For example, output, floor space, whatever it may be, or a combination out of that. What is also actually a big lever we saw is a minimization of the investments. So talking about AGVs, AMRs, or even workpiece carriers, they're actually one cost driver which somehow is not on the very top priority of many companies, but we saw that there is a huge cost reduction if we start in an early phase and really challenge on how many AGVs, AMRs, workpiece carriers we really need in order to achieve the desired output time. And also what we test here is inter-machine interdependencies. I have some examples on the next slide. In the end, it's all about how we get validated and robust concepts at a really, really early stage. So it's really about during our acquisition phase, we already help the customers to see and to check whether the concept is working or not. It's about lean footprint and reduced investment. And we're here not just really heavily using the Siemens tool chain. What you see here in the video, it's not just a rendering, it's actually NVIDIA Omniverse digital twin or visualization of current projects. So we're really already using also NVIDIA tools here in order to do this value stream simulation in the very beginning. If we now look a bit deeper and go one step further in the value add of such a machine. Now oh, sorry, I missed that one. So here we have the examples of the value stream, and I just want to bring some highlights here. So not all of them are, to be fair, coming out of battery business. So we do have here on the left-hand side an inverter project. And here actually what we really checked was this inter-machine dependencies I was talking about. Because here we do have many dispensing and potting processes, and they are crucial then for the later on processes, because we have sometimes restrictions in potting or curing time. And with that simulation here at the very beginning for this specific inverter project, we discovered some interdependencies with machines, and we already saw on how to solve it. So at a very early stage, we knew there might be a bottleneck between the dispensing process and the subsequent processes due to the curing time of the material. And we were really early able to find countermeasures and solutions in order to get good parts in the subsequent stations. Similar example was here in the radar sensor production, where we actually discovered that there might be an issue between the glue which was used there and the targeted cycle time and the process steps the customer was asking us, because we saw that there was no solution at all in this rather short curing time of this specific glue to run all the processes the customer was asking for. So together with the customer in a very early stage, we were then looking for different material in order to be able to both fulfill the requirements of the product, the glue, and the part later on. And the right-hand side, this is a specific example coming out of the battery production, where, for example, buffer was a big topic, and with these really early value stream simulations, we were really early in the project quite sure that we can also achieve the targeted machine autonomy with a really small footprint of the line. But now let's look a bit deeper into the virtual commissioning. So now we're talking about station level. And what we're doing here is that we really check the function of the station and the machine before we even start building it up. So it's not so super new on the first level, because checking for collisions and movements of robots, this is done quite a while. But what we're doing here is that we really apply the real PLC code. So even if the mechanical engineering is not even 100% done, the software department is already starting with the programming. And once the guys with the mechanical engineering are done, we can already challenge the PLC code on the system in the digital twin. What we also check for sure are the full kinematics, all the movements in the stations, linear axis and robots. And what we also check are special modes. What happens if someone is pushing the NOK button or the emergency stop in a certain position? How is changeover looking like? What happens if by accident the worker is putting a wrong part into the machine? All these modes we really check. And what we also check, in case the customer is providing us with an interface, is the communication between the station, the line, and the customer's MES. Because this is actually, in the end, very often a painful learning when we have the machine in place and then discover that we have communication problems with the plant MES and the station. And this is what we check in very advanced. And I want to give you a concrete example. We recently delivered a project where we decided, also out of our interest, that we, for the critical automated stations, we do this virtual commissioning full scale. And we provided this data to our customer in terms of pre-acceptance and shared the data. And they were so convinced of this benefit that they, in the end, decided to give an additional order to us to make this virtual commissioning for all automatic stations and even the critical semi-automatic ones. So it's really a big benefit, which is also convincing our customers that they decided they want to have an even bigger footprint in terms of digital twins of the station. What on top we're doing we are using Gen and agentic AI for software programming. We have at the moment a pilot project running, so it's not 100% in realization, but we are already doing it as of now. Using, and this is the advantage we have being in the Bosch group, we have the backbone of Bosch and therefore also access to AI agents and models which are also on high level of security. So all the data we have there, Google, Meta, or whomever you want to call, has no access to them because they're secured on the Bosch server. And with all these agents, we're at the moment already doing trials on software programming. So for the current pilot project, we already achieved a level about 60% of the POC code was done by Gen and agentic AI. So just the lasting 40% has to be done from our software programmers. And for sure, in the end, the target is to get to a level of 80 to 90%. The specific details will all the time have to be done from humans. But if we can do the basic task with Gen and agentic AI, this is helping us again in terms of reliability, costs, and speed, because these programmers can work 24/7. So this was one example and kind of an insight on what we're doing with software and digital solutions in our engineering toolchain. As promised, now I want to dig a bit deeper into what we do have on the operational side. And here I have an example about self-adjusting machine. From our experience and from our opinion, industrial AI will fundamentally transform the factory operation. And this is why I said for us the basis is actually the system digital twin, meaning the engineering digital twin we use in the engineering phase, but also the operational digital twin coming out of the factory. And our vision is that this system twin is created from manufacturing, system engineering, mechatronic engineering, and domain know-how, being especially process technology. So at first, heads up on what I will show you in the next slides. When we talk about self-adjusting machinery, what is it about? It's about that we have process parameters and also machining strategies which are actually determined automatically and autonomously from the machine, based on the not based on trained models, but based on physical models which are behind. And therefore, then the system in the end can automatically detect if there are any deviations in the results of the process, and then adjust the parameters accordingly to get back to the target state. In the end, this is all then helping us in robustness, giving a higher OK output rate, and also for sure increase overall production efficiency in the equipment of our customers in their shop floor. Now looking a bit deeper into what was the distinct processes, and here I have to apologize, the example is not coming out of the battery production. What we have here is a process where we do laser ablation. And we have here a multi-stage laser process with a high volume ablation. So meaning we have to remove more than 10 cubic millimeter per structure. And in addition to that, we have a requirement with high precision finishing, meaning the counter accuracy and the roughness has to be less than 1.5 micrometer. So this is the challenge about the ablation. And in addition, there's a welding process inside where we also have to do a real-time quality assessment about the laser joint. So how is this process now looking like? So first we have the laser process itself. The laser process itself is kind of conventionally done, so we have a set of parameters, they're applied to the part. Then we have a subsequent measurement, and all the data are gathered. These data are then analyzed with an AI-supported function, and then with all these physical process models having in the background, the system is actually adjusting the parameters accordingly without any influence from the worker, and even with the worker really don't know what the machine is actually doing in detail for all the specific working positions. The result of that is that we have this hybrid laser process with a fully automated measurement and a AI model which is evaluating the parameter and the process strategy. So the machine is actually self-adjusting itself. We do have realized ablation rates being bigger than 0.5 cubic millimeters per second. And actually, we achieved really high values in terms of surface quality, meaning less than 0.5 micrometer, actually having 6 sigma less than 5 micron for that specific application. And for the welding, actually the joint quality was on the same strength value as the base material. So it can't get better during the process, so we achieve the best what we can get. So what are the models and details behind, so how we did do that? So we actually used 3 different AI models. So first we had a large language model for the process software development. Then we applied deep learning strategies for the sensor data and the overall analysis of all the gathered data, and the machine learning algorithm in the end for the dynamics of the adaptation of the process parameters. This is all then leading in the end to a 0 failure rate, the welding with a reduced scrap, and until now we do have a 100% machine uptime with this specific machine. The machine is in production since 2024, so already since roughly 2 years the machine is up and running. And to show you that I'm telling the truth, here's now a quick video on this specific process. As mentioned, it's not in the battery sector, is in this specific matters wafer processing with an etching to in the end generate smart glasses. And here we used an engineering model, which is a physics-based model in combination with sampling, which is focused on different areas of uncertainty. So now you saw the etching process of this specific structure of the ablation process. And after this process is done, the wafer is moved into another position, where then a vision system is measuring the output result, and with that data then applying autonomously the next set of process parameters in order to get a maximum yield and the built-in robustness in this station. So this is the one example I brought for today about the self-adjusting machine. To give you a short glimpse on the rest of the portfolio, I just brought this overview here. Here you can see the different solutions we have in the so-called intelligent production suite. So here we do have different applications, software solutions can be operated on our machines in the area of transparency and analytics, of operational continuity, or if it's about control and optimization of the process and the output rate. To sum it up, we see that it's actually the new normal, that we have to get radically more efficient and cost efficient with the solutions to succeed in the global competition, especially in battery business. And our answer to that is, first of all, mechanical excellence. This is the foundation. This is the body of what we deliver. Yeah, so it's still about having innovative hardware solutions, bringing new technologies into the field in order to reduce cost, footprint, and delivery time. But this is, from our terms, not sufficient. This body also needs a brain. And the brain is actually what we say, it's a digital intelligence. It's about software-defined manufacturing as a key to enable us to be cost competitive. Applying AI to the equipment, getting self-optimized processes, getting a full scale of digital twin, this is then really moving us forward and bringing autonomous production systems to life. And the symbiosis of both these topics is actually what is then the difference and what's differentiating us and helping us and our customers to get really this efficient and reliable and robust processes up and running in the production. As I started at the beginning, it's about both. Yeah, we need first-class automation technology, but we also need software-defined production system. Because, again, this is then the decisive answer to the biggest challenges we're facing in the industry, and to get radically more efficient, cost-effective, and getting a scalable battery business up and running. Here I want to close my presentation. Thank you for your patience. I'm here, I'm happy to answer your questions, but also if you want to dig deeper, you're always welcome to visit us in Hall 1, booth E10. Me and my colleagues are happy to go into more deep discussion with you. Thank you.